And like one of the really interesting stories was how like the Romans would like sometimes get secrets across, Europe and stuff like that. And often, or sometimes they would shave the heads of messengers, tattoo their heads, and let their hair grow back, and then just send them out. So obviously, if anybody knew about this, you just get a messenger, shave his head, and you'd read off, whatever the secret message was. But the idea was, if they have hair, if they're passing through, like you can look at them, you can pat them down. They don't seem to be carrying any information. And this obviously has developed over like literally millennia. And the idea is always you're like hiding information kind of in plain sight.
Hey everyone, Jack is back, and today we're going to be talking about EvilModel, hiding malware inside of neural network models, which is I believe, a pair of papers that have come out. One came out in an IEEE conference and seemed like a cool idea, so I wanted to go to my source on all things data security, deep learning, machine learning, all that stuff. Jack, welcome back to the show.
Thanks very much, Glenn. Great to be back.
Yeah. So basically, way back when I first saw this article, I read the abstract, and it's the idea that they are going to be how to encode malware into neural nets. And this is very interesting because, when you think about, let's say, like a linear regression model, the question would be, well, how would you even embed malware into a linear regression model? It seems strange. But when I actually read along, I was like, oh, actually, that makes total sense of how you might actually embed malware into a neural net without anyone noticing. So I was wondering, maybe just to start, should we describe the concept of how they do this? And then, is that a good?
Yeah, I think so. Yeah, I mean, I first kind of maybe caveat that I don't think this should be like a fear necessarily of many people. It's an interesting idea, but it's really been one that's been around for like literally thousands of years. So it's the concept of steganography, which is literally hiding information basically in plain sight.
Yeah.
So maybe just as like a recap in case. So one of a book that I read, actually my brother had it, and then I read it like many years ago. And when I was moving, I realized I have two copies of it. So they have different covers, but it's the same book. It's called The Code Book. Simon Singh, I think it's pronounced Simon Singh. And they go into the history of cryptography and steganography from like Roman times, etc. And it's a super interesting book. And like one of the really interesting stories was how like the Romans would like sometimes get secrets across, Europe and stuff like that. And often, or sometimes they would shave the heads of messengers, tattoo their heads, and let their hair grow back, and then just send them out. So obviously, if anybody knew about this, you just get a messenger, shave his head, and you'd read off, whatever the secret message was. But the idea was, if they have hair, if they're passing through, like you can look at them, you can pat them down. They don't seem to be carrying any information. And this obviously has developed over like literally millennia. And the idea is always you're like hiding information kind of in plain sight, which is different to cryptography, by the way. So cryptography is typically, it's very clear that there's a packet, but you have manipulated it in such a way so that you can't work out what the hidden message is. So steganography is definitely pretty much most of the ideas in this paper, I wouldn't say are new, but I don't mean that critically to the authors in any way, by the way. I mean, a lot of the concepts are very similar to things that you'll have read in many papers in the past, typically relating to like images or like audio or text. Do you ever see those movies or like those kind of stories, and somebody like opens up a novel, and on page 123 or something, if you read the last character of each line, it says something that's a secret
you
message.
Start worshiping Satan or something like that,
or where the hidden treasure is or something. So that's all basically steganography. It's like hiding information in a certain way. And actually, in the paper they talk about different ways that people have tried to hide information in neural networks in the past, which is like it's exactly what people do with images and stuff. So the most straightforward way And I should just emphasize as well, this is just storing information without it being obvious that you're storing information in a neural network. That's the emphasis of the paper. It doesn't mean that there's malware that's going to get executed on someone's computer. These are two separate things. You still need some piece of software that would read out a set of bytes, accumulate them together into a program and then run it.
Yeah, that's something that I was wondering about. It's like, okay, I can get how you can encode the information, but I wasn't sure. It's like, surely there would have to be something else that would read it out. But anyway,
exactly. Yeah. So, so least significant bit is the first thing that they talk about, right? And this is something that, this is exactly how it was like originally done in images. So, like if you have an image, for example, and people use like RGB, so you've like 0 to 255 values typically for each pixel, and you got three values per pixel for R, G, and B. Or you could use one of the other color schemes, but like, so if you were to change a value from 2 to 1 to 222, do you think your eye is going to be able to catch that?
No.
Almost certainly not, right? So what they realize is the least significant element, or pixel value, is basically indistinguishable for most people when you're like looking at an image. And so if you just change those least significant bits to 10, 110, 11, whatever, then you could read that out as like a byte string, and that byte string might hold the contents of a computer program or of a secret message or of whatever. The exact same way as if you opened a book and on page 123, the last letter of each line spelt out a certain place where the buried treasure is or something, right? So that's really the basics of this. And so, in a neural network, you have lots and lots and lots and lots of values. And often, a lot of them are trying to be robust to small perturbations in the data anyway. So the least significant bits make basically very little difference often. So you could go around looking at all of your neuron weights and changing that like last least significant bit, +1, -1, or whatever, in order to hide a message if you were just to read out like the last bit of each byte of each weight in the neural network. So that's the least significant. Now, what you get out of that is just going to be basically a byte string, like a big set of bytes, which may be an executable. Now, obviously, you need a piece of software to read that out, and then you would need a piece of software to, convert that into an executable. So you would need to read it as an executable and then execute it, right? So it's like all of that is obviously a separate step. And what they're doing in this paper is basically saying, there's other ways that you may want to do it that could be effective as well, right? So, we can go into the different approaches and stuff, but just from that is like, does that seem clear?
I like that a lot. So, for example, the like maybe 19th century spycraft would be something like, here's the Bible, and you read off, like you'll go to this chapter and you use these words, and you'll have like a key, and so effectively you can, for example, take these words and use it to create a message, and you're hiding it in plain sight. Effectively you could take the article itself and just send you something where it's like, oh yeah, here's the thing. Actually, that's getting to a little bit closer to cryptography, yes. But this, so for example, with the neural net, you'll have these layers, you'll have the parameters, and the idea is if you have a 32-bit floating point, that if you grab the last bit or the very last few, and essentially you co-opt those for your need.
You just switch them into either a 1 or a 0, for example, depending on what you want to put in there. So you ignore the original value usually.
And also part of, I guess, this issue is that it's not going to affect the performance of the neural net very much, because it's, if you're going out to the very far ends, it's not going to affect its predictive performance. And also, just one other thing I was wondering about is like the issue of like dropout, where there might be so much redundancy in some of these things.
That's literally their second approach.
Yeah. Cool. So we'll carry on then, I guess.
No, because like what you're saying is exactly correct. So like if you think of dropout and how you typically try to create redundancies in neurons, that is what they propose as number 2, right? So the idea basically is that you have a whole bunch of neurons that you don't actually need in there. So what if you just replace them with, obviously instead of changing like bit by bit, you could just stick in, a chunk of bytes that you want as a particular neuron. And you could just retrain your network holding those ones constant. And basically they'll kind of be ignored by your network overall, or they'll be like compensated by other, weights in different layers of the network or whatnot. However, what you've done is you basically just, now if you have a lookup of which neurons to look at, you can just see, some index block number bump by bump. If we read that out, we get a big chunk of bytes we can stick into our byte string, and it's the exact same as the previous.
Cool. And just, I guess, to bring it back, if someone was like, well, why can't a linear regression do this? I guess the answer is you could. It would just be a very short, boring message.
Well, no, it could be a really interesting message, right? Because if you think about it, like, again, most people are sticking to like 64-bit precision, right? But why would you necessarily need to do that? So if you draw a line, right, you could say, that's just a line. What do you need for a line? Probably either 2 points or a point and a
slope intercept or something.
Exactly. Yeah. Slope intercept. So you could write that to, 10,000-bit precision.
Right.
Right. Mm-hmm. And everything after the
second decimal place
is not going to matter, right? Yeah. Like, I mean, it depends what you're using it for. If it's super high precision or something, but like typically speaking,
if it's for astronomy, probably not. But
yeah, exactly. Yeah. So then you just take out all of the rest of the bytes that aren't actually used, and maybe that's your secret message, right? I mean, there's always ways that you can kind of like put stuff in there.
Yeah.
So yeah, you're right. If it was like 16-bit precision or something, well, maybe that's quite limiting. So any small change will have like kind of a radical difference to your linear model. But actually, if you were to use enough bits to encode those two values, then of course you could have a secret message in there, and you probably wouldn't even notice it in terms of like overall accuracy, etc.
Yeah, actually, this reminds me of we'll just go off on a quick tangent. That I was talking to somebody who mentioned that one of the active areas of research is like 8 float research. So basically, if we essentially reduce the precision of the numbers that we're dealing with, mm-hmm. we can save a huge amount of memory, a huge amount of RAM. And it's like, okay, what is the trade-off between that? Essentially, and like, can we get way more out of it computationally if we basically trying to turn everything into like a 64-bit float?
100%. So that is quantization, right? Yeah. So this is quantization is the space of what you just described. So like you might have like big numbers and all the weights and all the rest. But what if you just bring them down to being only a small? In an extreme case, what if they were all binary values? Right. So everything was like a 1 or a 0. In which case, the footprint overall of your model will be much, much smaller. But of course, if you just listen, I may as well just explain to you. This is
go ahead.
Separate total tangent territory. But if you have a big model and you want to have a small footprint, right, to be like highly efficient for one reason or another, it's kind of like 3 ways you can go about it. So one is quantization. So you take all of say everything's stored in 64-bit. Well, what happens if it's like 8-bit or something? And for certain hardware, that also makes it way more efficient. So that's like it could be a huge speed up. The second is like sparsification. So all of the weights that are like almost 0, literally drop them to 0, or force them to be 0. So there's less multiplications and additions, and that will make throughput a lot quicker. So you can do like sparse matrix multiplication, etc. And the third is like model distillation. So you take a parent model and you have a much smaller student model, and you try to essentially train groups of layers, etc., to mimic the same kind of inputs and outputs. But often it just seems like, this is one thing that's really interesting, is that when you have like larger, deeper networks, you can optimize something that's useful. Whereas with smaller networks, you kind of get hit in local minima or something. But if you're training it based on the outputs of the larger network, then you can actually get to very similar performance. And that's like model distillation.
Oh, that's interesting.
Originally, like Hinton was involved, and I mean, there's a number of papers at the beginning. There's an author whose name is just not on the top of my head, who I think did the original Kurana or something, who did the original paper. But they're both like super famous research. I mean, and there's a lot of work. If you check out companies as well, there's a lot of There's one startup in particular called Neural Magic. So they spun out of MIT. They're really cool. I know some of the guys in there. And they're doing like really well, really quickly. I think they just been not around that long, and they've already raised like 50 million, and they're doing all sorts of things. And they literally take deep networks and they sparsify them, and they prune them, and they all of these kind of tricks, and they make similar performance on CPUs that you get with GPUs otherwise.
Wow.
I mean, that just totally changes what you can apply.
I now appreciate their valuation.
Yeah, exactly. Yeah.
That adds up.
Yeah. So all of that stuff, I mean, typically that all of this just kind of shows you how robust is probably the wrong word, but you know what I mean? Robust in quotation marks. A lot of these networks are to modifications and perturbations. And so if you have anything that's big, that has a lot of entropy in there, or perceived entropy, like there's a lot of stuff that's either random or looks random, then you can use that to just hide stuff. And that's basically what these guys are taking advantage of.
Yeah.
The third approach as well that they use, which is kind of similar again. Yeah, I guess this is like a fairly obvious one as well, is like if you have blocks of bytes that look like the blocks of bytes for your malware, sometimes you only have to change them by a few small values to make them a one-for-one match, in which case you don't have to modify your neural network that much, but you do need to have a lookup table to know which blocks to read from, essentially. And that's basically the third approach that they talk about in this in that paper as well. EvilModel.
Yes. Cool. And what and I guess one of the other bits that they mentioned was that like the architecture obviously doesn't change, where effectively you have so much real estate, if you will, that the architecture doesn't change. And I guess one of my questions for that was, does that mean that malware is really only looking, or some like malware detection is only really looking for like changes in architecture and things like that? Is that a major blind spot, or is that something that
so you're like the typical malware detectors don't do most of that stuff, I'm totally honest. So like this kind of comes back to like input validation, right? So when your computer receives something from the outside world, or a server, maybe it's probably a better example, you want to check and make sure that it kind of conforms to the structure that you're expecting. A lot of people don't do this, and then you have massive security bugs. So if we just think of like the history of this, I mean, there's a huge history, but if we think of like recent histories, right? So one example would be like, what if I sent from my computer to your computer a file, and it was, I don't know, it was like called, photo
Jack.
from our
PNG.
holiday.jpg, right?
Yeah.
And you're like, oh, it's a JPEG, or it doesn't even have to be a JPEG, PDF or whatever. So like the most obvious thing is what if that is not a JPEG at all? That's actually an executable. And when it runs, it does something bad and malicious on your computer. But I've just put in .jpg because I can just change the name of a file pretty easily, right? So something bad on your computer would then change that back to being an executable and would run it as an executable, and then that's obviously you don't want that. So one thing you might want to do is look at the file format the file is meant to be and say, does the file follow the structure of that thing, right? So an image or a PDF or anything like that has like a relatively strict like structure to what that should look like. So there is a header, and then there will be some information within the header, and like in a JPEG there's the EXIF data, so that's like a string that will tell you like maybe what camera it was taken on or something like that. You might have a timestamp of when it was taken, etc., or how it was processed, anything like this. So you can just check and say, like, does this follow the structure of the type of file that I think it's meant to be? And that's like one level of filtering that you can do.
Is that presumably like one of the most basic? It's just like you say you're a JPEG. Do you follow a JPEG format?
That's literally, yeah, like
It's
that's
like
literally,
you say you're an XML or whatever. We
yeah,
can look.
we can just check if you.
Yeah.
So that's input validation. So if you use, if you create a server that like people send JSON data to, right? So JSON format.
Yep.
JavaScript object notation. So typically, if you want there to be a JSON schema behind that. So if you build something in like Fast API, then you might be using something like Pydantic to check the inputs. But like pretty much every language, there's pretty much always a JSON schema tooling that will help check to make sure that the JSON you've received matches what you're expecting. So if I'm expecting your name and your age, I might check that your age is indeed an integer and it ranges from 0 or whatever the minimum age is to, I don't know, 100 and, I don't know what how old people can live nowadays, but to 150, right? No one's over 150. I might check that your name is less than so many characters. Maybe there's some limitation on that, and that all of those characters are indeed letters. They're not like, invisible characters, etc., etc. So you can literally just validate that the inputs you gave me match what I'm expecting, and that removes like a lot of downstream threats, or like you haven't done something. Like the famous example of this is SQL injections, so SQL injections.
Yeah. With the I'll pop up that KDX comic for the SQL
Sure.
injections. But yeah, why don't you describe it to people?
Yeah, so SQL injection is just like when you send SQL to your database, if you don't check it, as an intermediate step, then there can be basically like an escape character in there that would like end a command that looks okay, like, select this from that, like a read-only command. And maybe it says like drop all of the records from a particular table. And so in doing that, obviously, you would just lose everything in your database if you ran that unparsed or unchecked.
Yeah.
So, obviously, that's a very simple example.
Yeah.
There's more complicated ones I can describe.
The joke was something like, did you actually name your kid Johnny semicolon drop tables all student or whatever, drop all student tables? Like, oh yeah, little Johnny tables we call him. It's like you just destroyed our database.
Exactly. So that's exactly what I mean. So they're like sanity checks if you think about it. And again, you're not looking at, does the name Johnny have OH end versus ON? Because maybe that like implies something secret to an end user. You're just saying, does the structure fit what you're expecting? And then like past that, there's a whole bunch of like file types which we like data scientists are particularly bad at using, which are sometimes unsafe. So
like pickles, for example.
I was going to say pickles. Yeah, exactly.
Okay. Oh, good. Yeah, let's talk about pickles.
Yeah. So do you know the issue with pickles? I'm happy to go through it.
Yeah. Why don't you just go through the idea of pickles?
Yeah. So when you pickle an object in Python, you like vectorize Python objects in such a way that someone else who has the same version of Python or same version of pickle can deserialize it and then get back the Python object in all its glory. Now, the challenge there is that within the class structure of a Python object, you can have different, like underscore name, etc. So, and so you can have, like, when you're being deserialized, etc., you can have a function that runs in the object, for example, or you can do something similar to that. So when somebody's unpickling it, I think they've actually patched this, but this was a really big exploit like a few years back. You can basically, I can send you something that's a pickle object, and as you deserialize it, it will just run a bunch of Python code, and you have no control. So it could literally run, and in that code, it could download something from a website, and then it could run it on your terminal, and then, you don't want these things to happen. So, so that is the issue with basically. I think they have patched that, so now it's safer in its deserialization, but that's like pretty much the issues and the problems with those file types is that is a valid pickle file, right? Like,
it's valid.
It's valid, right?
My sort of like caveman understanding of it was that basically the universality of it. So all the extra functionality that makes pickle so useful is also like, oh, well, there's the poison pill in there too.
Exactly, yeah. And so a lot of people are moving, especially for deep networks, to like ONNX files, ONNX, things like the Open Neural Network Exchange or something is the, but you can pretty much like Keras, PyTorch, Piano, whatever. You can save things now to ONNX, ONNX format, and that uses protobuf. So protobuf is what's used in gRPC as well. And basically it has like a tighter schema around all the like values that you're expecting to share. And that's actually just to be more efficient. So you need less memory to say what each things are if they fit to a schema, right? So,
that's interesting.
Yeah. So, but because of that, you can check to make sure that like all of the values are correct and in range, and there's no like executable in there, etc. But of course, that doesn't solve the problem if you have like a whole bunch of weight values. They're just numbers, and who's to say a number is malicious or not, right? It's only how you, what you do with it, like how you interpret that number. And if you interpret in such a way that you can extract some value, that's obviously
bits don't cause viruses, interpreters cause viruses.
You know what I mean? Like, yeah. Kind of, right. It's not. Yeah, it's like if you look at like a dangerous program is only dangerous if it's run to some degree, right? So like the ones and zeros that it's composed of on their own aren't, like letters aren't bad, but you know, if you compose them in such a way, you get you get hate speech and stuff, right?
Yeah. So it's like colors in themselves aren't bad, but if you flash them up a whole bunch, like that Pokemon episode, you're gonna get kids with seizures. Yeah.
Exactly, right. Yeah. So exactly.
Yeah.
But I think what this brings back, and I think this is like really important, is actually this is really related to like the data science, machine learning, statistics community more widely, because it's all about information being present in something, and you not necessarily knowing that it's there or not. You don't necessarily know what to look at. And in a sense, we kind of do that. That is like the setting for a lot of the like ML AI stuff that we do. Like we don't know necessarily what the signal is, but we try to figure out if we can look at the structure of data in one way or another in order to find a pattern that allows you to do something. So like I think some like really interesting examples are, there's so many papers and examples if you look online. But if you take a video like this, like us talking to each other, and people look at like our faces, and they look at the change of entropy in like the kind of red spectrum, and they amplify that, you can work out people's heartbeats just from regular. You've seen this, have you?
Oh yeah, no, because at the IBME, basically when we were doing, basically I helped out with one of those studies.
Okay, awesome.
Yeah, but go on. Yeah, why don't you explain it?
Yeah, well, like that's literally the explanation.
Yeah.
You know, you look at like the fluctuations of like in color space of pixels that appear to be skin pixels, and you try to from that look at a frequency.
So it's basically like the pulsatile information where even though the human eye can't pick it up, you know, if you get a good patch of my pasty forehead, your human eye can't pick it up, but there is blood flushing through my forehead at a regular interval. And so effectively by picking up the differential on that, you then essentially have a pulsatile signal. And the other nice thing is that, you know, you have multiple patches that you can do it. So effectively you can be collecting it from different things. The signal will get messed up, for example, like if you like really like bleached out my head. So if I turned on the two like face lighters that I have that we have, that I don't turn on now because my eyes are so dry from coding all the time. But, you know, like you can bleach it out with the ambient temperature or ambient light. But yeah, it is really cool. But you can definitely transform it and see that pulsatile information.
I was always curious if you could like do that to politicians to like identify if there's any correlation between like heartbeats and whether or not somebody's lying or not.
Oh, I think that they're such like dedicated, like smooth operating liars that it doesn't even register with them.
Yeah,
and the other point is that you get people who are so, we'll just say substandard, that they don't even know that they're lying at some point. You know, you get the box that doesn't know that it's lying.
Yeah. Sure. Well, anyways, I think that's like an example where there's information embedded in something, but you only know it if you even know to like look for it to some degree. Another really, really cool example of like using information that's not like obviously present, and it's these are the things in the kind of like lower frequency spectrum, like lower bits, ultimately having like higher importance. Is what like MIT lab did in 2014 or something, but they presented at the Tübingen machine learning summer school, which I was at, and my mind was literally blown at the time. And what they did was they started with sorry, I realize this might seem like it's total tangent, but to me, this all fits together super closely because it's the small details in like high entropy signals that can have importance. And in the paper's case, its importance is that it's malware. But I mean, it could be anything. It's just bytes of information, right? And in this case, what they did was they started with like high speed cameras, and they would look at like a plant in a room, and from the vibrations of the plant, they would be able to pick up the audio signal. And they did it as well with like bags of crisps and stuff like that. So they would look at an empty bag of crisp just like on the floor, and from that they would be able to kind of like tune in the conversation that was happening in the room. And then they showed that you could even do it with regular like DSLR cameras. If the camera was really steady, the shutter speed of the camera, and because it doesn't go smoothly over the entire frame in one go, you can like look at the kind of like wobbling effect from this and pick up like low fidelity signals of what the noise in the room was. And I mean, that's just insane, right?
Yeah, no, that is ridiculously cool. It is nice to see one like the universe continuing to fit together. And then secondly, and we can pick it up.
For sure, right?
Yeah.
And like those type of applications, I would say a lot of the lower significant bits, to some extent, is actually those things that, when averaged over kind of a large collection, have a lot of information in them, right? And that's what you're using to detect audio or someone's heartbeat or whatnot. And there are like limits to it as well. So there's a thing called the shot noise limits and stuff. And it's basically like, as a statistician, if you're looking at, say, this background here, which is it's a white ball. I'm not sure if it's coming out white in the video, or the background behind you. If I was to look at the like,
that's salty dog blue, by the way.
Salty dog blue.
It's salty dog blue.
Yep. You become a lot more posh since you left university days. But if you were to look at the like least significant bits of them, you would kind of expect it to be like Gaussian. And the idea is that you can hide information by changing those values as long as it's kind of like within kind of one standard deviation. If it's more than that, someone might be able to pick up that it's like very high entropy and identify that there's a signal in there. But that's, I mean, this is all law of large number stuff. So it's like, I think the rate is like 1 over square root n or something, which makes sense because that's how standard deviations decrease with sample size.
Yeah, that is cool.
It's all super linked. It's all information theory. It's all, it's much easier to create, a signal, to do steganography, than it is to identify that something's in there. And most of the things I would try to like catch, either they're looking for a pattern that they know in advance, and so they're looking at things in different ways, or they have some insight on how the person might be doing it, but it's very difficult to. If I show you a picture, it's very hard to know. I mean, even with human level cognition, if someone has changed bits or modified something very subtly, that means that contains some information that seems random to us, but is like, in fact, an encrypted executable package or something.
Would there be any value, like, there's examples where you can change, say, one pixel on an image, and it goes from looking like a panda to the neural net thinking it's a bicycle or something like that, where effectively they'll have like super. I don't know enough about this topic to know if it's like if these are just really well curated examples, or maybe it's that they don't just change one pixel, they change a large number of ones where you can still see it for what it is, but it's enough to mess with the algorithm. So maybe
the adversarial noise, basically.
Yeah, I guess part of me is things like, well, would one way to fight against this be basically we take anytime you take a neural net, you essentially just jitter its parameters vaguely, and that would be enough to probably like break an entire program that might be in there. Would that be sufficient, or is that dumb?
So you're just saying if we believe that the least significant bits aren't that important, you're saying why don't you jitter them? Or in fact, you could just remove them, right? So you could just try to quantize your network so that you have less bits. So most of the bits are doing more work. So perturbation or changes to them have a larger effect. Sure. Yeah, I guess you could do that. But like I think the challenge is still that there's a lot of things that appear random, and if things appear random, you can kind of add other things that appear random, and it's hard to spot.
Yeah. Oh, I'm not talking about sort of trying to spot it, just saying like as a precautionary measure, when we have essentially if someone sends you a neural net with all its parameters, would there be something where effectively you can just jitter them? And like if you made it a standard where it needed to be insensitive to a certain level, that effectively you could just jitter them and thereby scramble any sort of malicious information that's in there.
So you could for the least significant bit ones, but like the other examples where they said like if you find blocks, like entire blocks of weights that are similar to blocks of bytes in your malware, and so you're just making small modifications to them, that might not solve the problem, because there's a lot of like error codes in signal processing and error in like electrical engineering, like software, like lower level software engineering, etc. So it might be the case that small errors actually don't make that, they can correct them post-processing or something. But I just want to be really clear here, right? What this paper is not saying is that they give you a neural network that is in ONNX format that looks totally legit, but when you send data through it, it suddenly executes something that you're not expecting it to do. What it's saying is that we can put some numbers in there that don't really affect performance. But if I was to read out those numbers by another program, I could reconstruct a program that, if ran, would then have a malicious outcome. Does that make sense?
Like totally does. So I guess the question is then they would need some other way to get to attach the reader to the information. Is that
for sure? Yeah. So you actually hear. I'm going to butcher this because I don't know much about this. Like this isn't. No people who might, but it's not me. I think there was like an issue where like Jeff Bezos had like received an image from, I don't know, someone on WhatsApp or something from like his.
Was this regarded to like his new girlfriend thing, whereas like he was getting the weird images sent that way, or is it just like some totally random thing where Jeff Bezos got Bob from Idaho's picture or something like that?
I'm afraid I'm going to butcher the story, so okay. I'm just going to say this might be an issue, right? So somebody, basically accidentally downloads a small program that gets executed on their device, right? Now, it's a very small program, and that's how it managed to get through the filters that are, right? Like it's not obviously spotted as malware or something. So it on its own is probably not very valuable. But then somebody starts sending you like videos or something like that. And this small program, all it does is it looks at every third frame and takes a certain set of pixels and constructs a much larger packet of information that's maybe now a couple of megabytes or something, or instead of a couple, right? So maybe it's like a larger program that can do something bad, and then it runs it, right? So that program that just constructs these bytes looks for a file with a particular file name. If it sees it, constructs the bytes and executes it or something like that. That probably is a very small footprint. So maybe you can get through the gap somewhere. But then when you're passing in much more like the larger like malicious content, that's the bigger payload, but that's like hidden in the weeds of something else. So that's hidden in the weeds of a PDF report you're downloading, or a JPEG image, or a movie you're downloading onto your phone or something like that, or onto your laptop or something. So I think that's the general structure of some of these attacks. And also, I would like to say I am not. I'm not a cryptographer or like security architect. I get to work with great people who are, but but this is like the kind of general structure of a lot of these attacks.
That is cool. Was there anything else in this paper, either this one or they had EvilModel 2, that paper? Was there anything else that would sort of be like essential or interesting to cover in these papers?
So I think EvilModel 2 kind of builds on the first one. And so some of what they're doing is they're creating heuristics to try to say, can we benchmark how well we can hide information? So I believe it's like the intersection of like effect on performance and how much, like the density of information you can store in a network.
Yeah, there are way more empirical results in the second one.
Exactly. So it's not a fundamentally different. I consider that more of like follow-on paper for more of a broader analysis of, can we formulate this more as a field so that we have something to optimize for kind of in the long run.
I thought it had some interesting, like it had some interesting discussion points if you're trying to basically visualize and understand these things better. It seemed like the EvilModel 2 paper, which I'll pop up on the screen. I don't know. It's just like if you really want to get into the weeds and have a high level understanding, EvilModel 2, I think, describes some things pretty well.
Yeah, absolutely. Yeah, like I agree. Yeah,
cool.
They kind of go step by step, and they give, I think, more empirical performance heuristics, and I think it is very like clear explanations. But I would emphasize that these things interleave and connect with a very long history of people doing very similar things, but just in slightly different domains. And so anytime you have a high entropy signal, you can always, this isn't like, Jack's law that you quote me on in the future, but like typically speaking, if there's like a big signal with lots of like perceived entropy to it, then you can hide stuff in that entropy.
That is very cool. Yeah, I appreciate. I enjoyed the conversation this sort of lead up email chain that we had before this, and I appreciate you taking this head on. So, Jack, thanks again.
Well, one thing actually I'll probably just leave with, which is this was because we wrote a grant for something, and I was looking around on different things, and we talked about like the heart rate. We talked about like listening to people speaking, or to a music or something based on like vibrations of like a bag or a leaf or something. One thing that I think is another area where there's lots of ever improving data and signal, and people don't necessarily think of the consequences of what relatively small pieces of information can lead to if used for the wrong purposes, is a lot of the like Earth observation imaging. Have you seen these like satellite images of Earth?
Like, I've seen the pictures, but yeah, go on.
I don't know. Google Earth or something, right?
Yeah.
So the precision is getting better and better. So you can buy commercially 30, and I think soon to be like 15 centimeter per pixel images. Like that's like
15
really
centimeters per
30,
pixel.
30 is definitely available. And I think there's a move to like 15, but this is like crazy detailed pictures of Earth. And you can just buy them. Like Digital Globe sells, like that's a big vendor of satellite images. I think Boeing and other groups also, I think it's Boeing, there's BAE, one of the big satellite companies also. So, there's there's lots of companies that I think you have to say your purpose is for it, but like, I mean, I'm pretty sure that's not a hard.
It's like my purpose is to destroy my storage space. Go on.
Yeah, exactly. Yeah. And there was a lot of stuff around sparse encoding, which is about kind of having mirrors in a certain way, so you kind of compress it while the image is being taken, so you can send it back to Earth, so that you could take pictures of like the entire east coast of the US or something in one go. But of course, you have huge memory footprints associated with this. But what I find really interesting about that is that, again, it's small detailed information that actually makes some of this stuff potentially quite dangerous. So I remember having a lecture in my undergrad where there was the lecturer was saying, what makes information sensitive or potentially dangerous. And it's like knowing that driving down the street or going on Google Street View and knowing that a particular house seems to have a new BMW 6 Series. Is that dangerous? Maybe it's not. Okay. But if I was to give you a list of like everyone in Pittsburgh who has a 6 Series BMW, a new one, and where their driveway is, and if that's what you rob, then suddenly that list is like your go-to of like where to find everything to rob. And I think more and more people are using like data sources like Earth observation imagery, so like satellite images, etc., and to learn more more details about so there's MIT does a treepedia, like a Wikipedia for trees, I think, and they look and count trees and rooftops in urban areas or something like that. And then NUS in Singapore did a similar project where they were looking at how many how many solar panels were on roofs of where they were, et cetera. And they would count them per city to see how green the city was. But I do think that this kind of goes in a direction where, like, if you look at the footprint of a vehicle, you can, like, especially when you're like high resolution, you can realistically tell what vehicle that is and what color it is. And a lot of that's just like publicly open, right? I mean, it's easy for anyone to buy. So it does start to bring up questions about like privacy and security and risks associated with it. In the case of EvilModel, your risk associated with low-level bits, and the structure, etc., is that could be collated together and used as an executable that might do something bad on your computer. The sets of pixels in like huge images of Earth, etc., that can often raise questions of, could people use that information for like negative purposes if it's like disclosed? And I think this goes all the way back to things like differential privacy, etc. Like if I have a database that's sensitive and I'm disclosing that information to others, how do I make sure that it's safe to do so? And I guess it's in a totally different guise, but EvilModel says a very similar thing. It's like, I guess it's the opposite of how do we say if a model is safe and lacks any malware. Instead, it's saying, how can we introduce malware? But if you want to be cat and mouse here, hopefully we get future papers to say, how do we detect if there's malware then in these networks, etc. So I just thought, like, when people, if anyone listens to this, if they think about the like data sets they interface with, they can ask themselves what's in the weeds and can this be used for like negative purposes, etc.
Yeah, no, it reminds me of that quote from the Joker who says, Gotham needs a better class of criminal. And now I can imagine that he has a little list in his pocket of a series of technical requirements that they would need to do to distinguish the signal from the noise of global satellite images and things like that. So that is cool. Yeah. Any other random cool idea? We have a little bit of time left, but do you have any other random cool ideas or anything?
I think so. I mean, one thing that I just really love is that all of these ideas come back to the same points. Like, you can be a statistician and you can look at cybersecurity issues, or you can be a computer vision person and you can think about, steganography, or you can be a biostatistician and you can be thinking about even before this call, we were chatting about like challenges with synthetic data, and sometimes there's modeling assumptions that basically destroy information that you actually want to preserve because you want your synthetic data set to be useful to someone upstream, but maybe you just want it to be safe from the original data set using some different privacy mechanism or something. And I think it's, I think it's really fascinating, like looking at the intersection of all of these spaces and like identifying this. It just shows that, like, especially people who aren't in the field, who are like coming in from, maybe they're starting their undergrad or something. It's like if you get like the fundamentals like down and you like think about like information theory and like interest in maths and statistics and probability and stuff like that, there's just so many ways you can kind of apply yourself. And even if you go down one path and you say, oh no, this is boring, I want to do something else, you've set yourself up for an easy transition, I'd say.
Yeah. And honestly, you might even have set yourself up for a better transition than if you've been going down that route the same way, because effectively you have the robustness from the additional perspectives, different methodologies, and sort of concerns.
Absolutely, it's like a cross-pollination of ideas almost.
Yeah,
fields.
Yeah, you're sure. like a hybrid pepper. Monsanto will come and steal you at some point.
Yeah.
Cool, Jack. Awesome. Yeah, as always, I really enjoy our conversations. I'm looking forward to the next one. And in fact, I'm especially excited because I have a good idea about what the next conversation topic is going to be about. And
I look forward to hearing your ideas.
Sounds good. All right, cool.
Awesome. Thanks so much, guys.
Thanks.